In today's lesson, we will begin to explore conic sections with circles. Our objectives are to write and graph the equation of a circle in standard form, given a graph, or a radius and center. Also to write the equation of a circle in general form, given an equation in standard form. Let's go ahead and look at what the definition of a circle says. A circle is a set of points, or a locus of points, that are equidistant from the center. And the center of the circle is HK, and in this case it's at the origin, 0, 0. Notice that the set of points that are equidistant from the center are at the end of this radius. So every point on the circumference is equidistant from the center, and that forms a locus of points. So what kind of an equation can we create that will define this locus of points? Well, you know that if this point is xy, then this distance going to here, that's our x distance. And then coming up here, that would be our y distance. Notice that we have a right triangle. So we can define r using the Pythagorean theorem. The Pythagorean theorem, remember, is just a squared plus b squared equals c squared. But in this case, our a, we would say is x, and our b is y, but our c is just the radius, so r squared. And this is the general, or I should say the standard form of a circle without any transformations for the center. So let's look at that. What happens if our center is not at the origin? In this first case here, it was. What happens if our circle translates down? Well, in this case now, our center is somewhere else. Maybe it's down here. So what we've done is we have changed where h and k are. We have translated that. And if you remember from graphing other forms of equations, whenever we translate, we add or subtract if we translate horizontally or vertically. Well, in this case, we have translated to the right and we have translated down. So remember that the center is always HK. That's how we represent x and y. If we want to show that translation, for x horizontally, we would write x minus h, whatever h is. And since we're going to be translating y on the same side as y, we could write it the same way. Y minus k, whatever k is equal to our r squared. So in this case, say we translated 6 to the right and 6 down. So we have a center at 6, negative 6. We would have x minus 6 squared plus y minus a negative 6, which is really y plus 6. So again, the concept of the opposite sign would still apply here with circles. Let's try defining a couple of circles. In this first case, we have a radius of 4. Here's my center, and I can count 1, 2, 3, 4. So I know my radius, and I can see my center at 2, 3. So I can write the equation of this circle. X minus 2 plus y minus 3, remember these are squared, is equal to our radius squared, or 4 squared, or I could write it as 16. Go ahead and pause the video and try to write the equation for the second circle. For the second circle, I can see that the radius on this is equal to 3. I can just count directly across. Notice that my center is at negative 1, negative 3, so I have x plus 1 and y plus 3. What happens if we have a circle like this? We really can't count because it's not a direct horizontal line to the circumference or a direct vertical line. Here's a diameter. So these are the endpoints of my diameter. How am I going to write the equation of the circle in standard form given this information? I don't know the center. Well, think about the tools that you have. If this is the diameter, then the center is in fact the center of the diameter. It's midway between them. We can use something called the midpoint formula that you've used before to find the center. So let's do that. Remember that the midpoint formula is just the average of our x's and the average of our y's. So we could take 7 plus 1, divide by 2, and get an x-coordinate of 4 for our center. We can do the same thing with the y's. We can do 6 plus a negative 2 and divide by 2, and we would get a y coordinate of 2. Once we know the center, we have many options for finding the distance of the radius. So we want to know how far it is from this point on the circumference to the center. We can use the distance formula to find that distance. We could have also used the distance formula to find the distance of the diameter and then split it in two. So let's go ahead and use the distance formula of this radius to determine what its distance is. Here's our distance formula, which is really just another form of Pythagorean theorem, except that instead of writing d squared equals x squared plus y squared, we have taken the square root of both sides. If we solve this, we know that 7 minus 4 is 3, and 3 squared is 9. 6 minus 2 is 4, and 4 squared is 16. This gives us the square root of 25, which we know to be 5. So now we know the radius and we know the center. We are ready to write the equation of a circle. We can write it as x minus 4 squared plus y minus 2 squared is equal to our radius squared, or 5 squared. Now let's go ahead and write the equation of a circle in standard form, but then let's graph it. At this point now, we can easily write the equation of a circle given the center and given the radius. So here's the equation of our circle, but how are we going to graph this? When we graph something, we need to write it in the form of y equals, and this is not in y equals. So we need to adjust our equation a little bit so that it's in that form. The first thing is to subtract the x minus 2 term to the other side. When I subtracted the x minus 2 term, I went ahead and simplified the 5 squared to just give us 25. Now, in order to get the y by itself, I need to undo this square, so the parentheses will go away and I can subtract 4. So what I would want to do is take the square root of both sides. When I do that, I'm going to be left with y plus 4. Remember that when I take the square root of something, when I'm solving for a variable, I'm always going to get plus or minus the square root of 25 minus x minus 2 squared. Now I cannot distribute the negative into the parentheses because right now the parentheses are being squared. So I would just need to leave this like this, or I could expand the x minus 2 squared. But for now I'm just going to leave it this way. It's more simple. Finally, and for my last step, what I'm going to do is subtract 4 from both sides. At this point, I am ready to graph this function. But notice I have a plus or minus. So really I have two functions. I have one with a plus, the square root, and I have one with a minus. Graphing each of these functions, I get a complete circle. Notice that on the top one I have the plus, the square root, which gives me the red portion of the circle, and then on the bottom I have the negative square root, which gives me the blue portion of the circle. If you think about a circle, consider, is a circle a function? Will we ever be able to have just one equation that we can graph that would give us the entire circle? So think about what you know about functions and why you have to graph these as two separate functions. So far, we've just been looking at circles in standard form. Now we're going to finish off by looking at circles in general form. So let's take this information and write the equation of a circle in standard form. And then I'll show you how to write it in general form. Here is our equation in standard form. In order to write it in general form, all we have to do is expand all the terms. So we would need to take x plus 2 and square it, and y plus 3 and square it, and then go ahead and square the 2. So we can either do x plus 1 times x plus 1, or we can use our shortcut. Anytime we have a binomial squared, we can take the first term and square it. First times second times 2, that would give us 2x. And the last term and square it. We can do the same thing with the y plus 3 to give us y squared, plus 6x plus 9 would equal 4. 2 squared is 4. To finish this off, we just need to rearrange this so that we have our highest degree variables first and our lower degree variables last. So we would start off with the x squared plus the y squared. Then we'd go back to our x terms, we're doing them in order, plus 6x. And then on this side, 1 plus 9 is 10, but then we have a 4 we need to bring over. So we would subtract 4 from both sides. That would leave us with 6. And that's all there is to it. So here is the equation of a circle, but now it's in general form. What happens if we start with an equation in general form? How do we put it back to standard form in order to identify the center and the radius? Well, if you'll notice, these are both squared terms, so we can really make two quadratics by completing the square. So the first thing is to put this in order of x terms together and y terms together, and then move every other term, our constant terms, to the opposite side of the equation. Now, once we've done that, we're in a position to complete the square. So we're going to complete it first for our x squared quadratic and then for our y squared quadratic. If you remember back, in order to complete the square, in order to have that perfect number here, we're going to take the coefficient of our x term, which is -6, cut it in half or divide it by 2, and then square it. That gives us 9. We'll do the same thing with our y term here. So we have 2, cut it in half or divide by 2 and square it. 1 squared is just 1. Now we can insert those numbers. So here's our 9, and notice that I've put the quadratics in parentheses so they're easier to see and work with. So I went ahead and added 9 to the left side, and I added 1 to the left side, which means I have to add them both to the right side. Now I'm ready to factor each of these quadratics. This is the easy part because I made up this 9 to be a perfect square. So to factor it is just the square root of it. So it would be, sorry, not that squared, it would be x minus 3 times x minus 3. That would be how you would factor this quadratic, but I'm going to write it as x minus 3 squared so that it's in standard form for a circle. For our y, we would get y plus 1 times y plus 1, or y plus 1 squared. On the right side, -9 plus 9 is 0. That leaves us with 1. All right, let's identify our radius. Well, our radius is going to be the right side, the square root of the right side, which is just 1 still. Our center, our HK, is going to be the opposite of what's in here. So we would have a +3 and a -1. Let's try one more example before we end. Pause the video and see if you can do this one by yourself. Your first step should have been to rearrange the equation so that your x terms are together and your y terms are together. Your second step would then be to find those perfect squares. So for our x term, we have -1, divide by 2 and square it. That gives us a +1/4. For our y term, we have a 2. We'll divide that by 2 and square it. And that just gives us 1. Now, for our third step, we can take these values and put them into our equation. So here we have our x quadratic, here we have our y quadratic, and notice that I've also added those terms to the right side. If we factor the x, we get x minus 1/2. The square root of 1/4 would be 1/2. If I were to factor it, I would get x minus 1/2 times x minus 1/2. And for our y, it would be x or y plus 1 squared. And then on the right side, the 1's cancel, and I'm left with 1/4. So our radius is going to be the square root of 1/4, because remember that our radius is some number squared, so to figure out what that number was, we would take the square root. Our radius in this case is 1/2, and our center, our HK, is going to be equal to 1/2, -1. And that concludes our lesson today on conic sections circles. So at the end of this lesson, hopefully now, you are able to write and graph the equation of a circle in standard form, given a graph, or given a radius and center. You also should be able to write the equation of a circle in general form given an equation in standard form.